In the third and last part of the lecture, we will talk about light. In fact, without light, there would be no vision. So, it is the interaction of material, of objects with light that make vision happen. If you look at that cartoon, if there would be no interaction at all, if the light would not be influenced by the presence of the person on the left, would just go straight ahead, then we would not see the person. But it's because the person will reflect the light towards the camera. That makes you see that person. So, vision, it's all about the interaction of light and matter. So we have to study that interaction a little bit, know a few things about it. So if you look at the storyline here, the storyboard, you have a light source upright, so it is the sun or the light in the room, and that light falls onto a surface, the yellow thing. Part of the light is being reflected by that surface towards the camera. The light goes through the lens, the blue spot here, and then falls onto the actual sensor on the left. That other parallel we won't forget about for the moment. Now, today, anyway, it's only about the right-hand side. The light, the illumination, and the surface, the object, the matter. This part. So first we will say a little bit about the nature of light. What is light? And then we'll talk more about those interactions of light with matter. If we study optics, we can do that at 3 levels of precision, so to speak. We can look at geometrical optics, and that means we are mainly dealing with the path that the light follows. Then we have physical optics. We could say that actually what is being added now is, most of all, how much light follows that path. So, for instance, upon reflection, how much of the light has been reflected. And then one could go for the most detailed analysis of light, a quantum mechanical optics approach, but that we won't do. In fact, we go for that second option, physics optics, a physical approach to optics. And at that level, it suffices to look at the wave character of light. We don't have to look at light as particles. So as soon as you go into the third option, quantum mechanical optics, you would have to deal with that dual wave particle nature of light. We don't have to deal with that. So for us, as far as we are concerned, dealing with the physical optics, light, that's a wave. What kind of a wave? Well, it all starts with a charge. A small charge, a particle, it has a charge and it moves. And that creates an electrical field. And you see that electrical field there, E, right? It's oriented in a certain direction depending on the motion of that particle, that charge. Now, as we know from Maxwell's equation, an electric field will then, if it changes, generate a magnetic field. So that's H here. So you have this electrical field, it changes over time, and you have a magnetic field, which also changes over time, and again, according to the Maxwell rules, will in turn generate an electric field. So here you feel it come, right? You cannot have coexistence of whatever kind of electric fields and magnetic fields. They have to be mutually compatible with each other. And it was Maxwell's genius to see exactly what kind of waves could coexist and what other properties these waves had to have. And the main type of waves, the waves that can propagate for a long distance in the medium, is of this type. It's a sinusoidal wave for the electric field and a corresponding sinusoidal magnetic field. So both are sinus types of waves, and they are also perfectly in phase with each other. They go through a maximum simultaneously, through zero simultaneously. And the whole wave moves forward orthogonal to that plane formed by these two vectors, the electric field vector and the magnetic field vector. This all follows from Maxwell, and we will not repeat that here. That's basic physics. Now, note that we are diving into the analysis of these electromagnetic waves, but that was another great inspiration from Maxwell, that he understood that light was nothing else but a specific form of electromagnetic waves, because before Maxwell people didn't understand that. Although they were playing around with electrical fields and magnetic fields. So what do we need to characterize a wave like this? Well, there are certain parameters that we need to specify. The characteristics of a wave are namely, in the first place, the wavelength. So how the frequency of these oscillations are. The wavelength depends on the color that we will see. So for us, perceptually, a wavelength is connected to a color. If you have a certain wavelength here, you see a certain color. The longer the wavelength, you get the more red. The shorter, the more green. You see that again. Very short wavelengths, bluish. And then longer and longer wavelengths getting more and more towards the red. We as humans can only see a small interval in that entire space of electromagnetic waves. There are only certain frequencies, certain wavelengths we are sensitive to, from about 400 nanometers to about 750 nanometers. Those are the wavelengths we can see. But there are, of course, shorter wavelengths, ultraviolet, X-rays, gamma rays, shorter and shorter as you go down. And on the longer wavelength side, you have the infrared, microwaves, radar, TV, as the wavelengths get longer and longer. But these we cannot see, okay? The second characteristic to characterize a wave is amplitude, and that is connected for us perceptually with the intensity of the light. So if you would now increase the wavelength, you see that green becoming more intense, brighter. You see again that these two fields, electric and magnetic, they are coupled in their amplitude. So these are two things we can see. The wavelength connected to the color, the amplitude connected to the intensity. And of course, light will have a certain direction. So if you don't disturb light, if it goes to an optically homogeneous material, it will just follow a straight path. But it will move. And it will move at the speed of light. Okay? So light shoots out there, going at the speed of light along a straight line. If the material is of the same type everywhere. Then there are things we cannot see. And one is the phase. And that's where, in fact, the pattern goes through the maximum and the minimum relative to that reference plane on the left. So this will be the phase of this particular wave. And different waves can have different phases. Now, you could have two waves, same amplitude, same frequency, but different phases. We cannot see that as humans. We are blind to phase. Another thing we are blind to is the direction of polarization. And that is the orientation of that electric field vector. It could have different orientations. This is now drawn vertically. In this case, we have a vertical electric field vector. So we have this vertically polarized light. And again, as humans, we cannot see the direction of polarization. Now, that said, we will see ways of exploiting the direction of polarization so that we can analyze flaws in a scene or the kind of materials in a scene more precisely and more easily than without polarization. Okay, in summary, having a wave, and I said it has these two components, there is the electric field and the magnetic field. Both are orthogonal to each other by the laws of Maxwell. That's implied by these laws. You see them also being nicely in phase relative to each other. What we now have to specify to fully characterize that wave are these 5 things. So we have the wavelength, determine the color that we will see, as we have just seen in the movie. Secondly, the direction of propagation, orthogonal to the plane formed by E and H, the electric and magnetic field vectors. Then we have the amplitude, related to the perception quality brightness. And then we have phase, and we have direction of polarization, to which humans are blind. Now, you may ask yourself, yeah, but usually what I see is white light, or kind of whitish light, whether it's coming from the sun or in a room. Well, in fact, that white light is composed of many different waves, different wavelengths, different phases, different directions of polarization. So what you see in white light is a summary of all these different ways of which it is composed. And you can decompose to some extent by shooting that light through a prism. And you see that on top there. So the prism is hit by the light and is then being spread out in a different wavelength. As a matter of fact, each of these wavelengths will be broken to a different degree. So there is a certain angle under which the light changes direction, and that angle is dependent on the wavelength. So a prism comes then with 2 of these transitions. So when the light comes out, it is nicely spread out in the different wavelengths. From on the top, the least bended part of the light, the longest wavelength, to down there, the bluish light, which is the most bended part. And again, we have mentioned that before. In fact, we as humans are only sensitive to a small part of the electromagnetic spectrum. So we are sensitive to about waves of 400 nanometers wavelength to about 750 nanometers wavelength, but not beyond. That said, you can form cameras with lenses and so on, that would capture light with longer wavelengths, infrared. So there are cameras that would measure infrared light, and also it's possible to measure with to capture with a camera ultraviolet lights. Okay. We mentioned the connection between wavelength and observed color. And here's a kind of transition table. So if you have wavelength on the left, like the top interval, 380 to 450 nanometers, people will see violet light. And then from about 450 nanometers to 490 nanometers, you see blue. And so on. You go to longer and longer, you see then green, yellow, orange, red. Now, the first thing to note, and that's maybe a bit counterintuitive, these arrows are directed. So you have certain ranges of wavelengths, and out of these wavelengths follow certain colors. But these arrows cannot be put in the other direction. So if you see a certain color, it does not follow that that light will only contain wavelengths in the intervals on the left. So from left to right, yes. From right to left, no. Okay? So that's that first no there. From the observed color, you must not conclude that the light only contains wavelengths as given on the left. So you have a color, you see, for instance, yellow light. That does not mean that that light will only have wavelengths between 560 nanometers and 590 nanometers. Because light in practice will be a mixture, it will give one overall color as a perception, whereas this table is for monochromatic light. So if you have light only of a certain wavelength, as seen on the left, only in those intervals, a single wavelength, then those colors will follow. Second note, cameras don't necessarily behave completely like the human eye. Cameras are made to be close to the human eye, but they are still not identical. And the big difference is that usually silicon-based cameras will have a sensitivity to near-infrared light. Humans cannot see that, but cameras can. So typically a camera inside will have a filter blocking out the near-infrared light. Otherwise you would get an image that is not really the way people will see the world around them. So there are differences in the spectral sensitivity of human vision and cameras. And by the way, not only between cameras and human vision, but also between humans and other animals. So, on the left, you see human vision on top. So we have actually, but we will come back to that in the section, the lecture on color. We have 3 different light-sensitive cells in a retina, cones, so to speak. And they have different spectral sensitivity. But that is range, right? About 400 to 750 nanometers about. There we have some sensitivity. For bees, that the whole thing is shifted. You see that on the right. The whole field of sensitivity is shifted to shorter wavelengths. So bees can also see ultraviolet, which we cannot see. But then they are not quite as sensitive to red. And birds are also interesting because birds, they also have a wider area of sensitivity. Also on the shorter side, they see things we cannot see. And they even have 4 different types of cells in their eyes, rather than the 3 we have. So their vision must also be a bit richer in that sense. Okay. So human vision is not the standard way biological vision works. There are many types of eyes with different spectral sensitivities, different types of resolutions, and so on. And for different applications, people also have built cameras that can see beyond what is visible to the human eye. On top you have an example of an infrared image. So on the left you have these transformer coils, and they will heat up. And in order to see that heating up, infrared cameras are being used. So if you go far enough, we are not talking about near infrared light here, we are talking about even longer wavelengths than that. So think that a normal camera would also not see. This is a specialized, dedicated infrared camera. It sees quite beyond the near infrared, which would be about 1 micron. So this is even beyond that level, where you have a connection between temperature and the amount of light, infrared light coming onto the camera. So you see that a heavy spot there in the center, indicated with red, very much infrared light reaching the camera there, a very hot temperature. And that allows you to make that distinction from a distance. On the bottom you see a satellite image, and it has 3 color bands, red, green and blue, on this display. But actually, red, green and blue don't measure red, green and blue. What is red here amounts to near infrared. So the near infrared, the reflection in the near infrared towards the camera on that satellite is shown as red. And the green corresponds to what is coming from the scene as red. That's shown as green. And the blue is actually the green in the scene. So if you see some heavy red here in this image, that means a lot of near infrared reflection. And it's typical for plants that they very heavily reflect in the near infrared region. So a healthy plant will strongly reflect near infrared, less red. So if you see a lot of red in this image, that means a lot of near infrared actually in the scene, and that means there are plants here. Indeed, these are all agricultural fields. You see there must be quite some heavy vegetation there because there's a lot of red to be seen. Like that, people can, for instance, also study the growth of deserts, or the opposite. For instance, the Amazon forest is actually growing for the moment. Also, there are more forests in Switzerland nowadays than before. That can all be studied in these satellite images. Okay, Now, this was about light. But how does it interact with matter? That was the second thing we wanted to look at. So here we will have 4 types of interaction between light and matter. The first is absorption. Light may just be dissipated and disappear. That's why, for instance, water looks blue, because the longer wavelengths are largely dissipated in the water. So they don't come out again, they just are dissipated in the water, absorbed by the water. That's an example of absorption. Then we have scattering. As we will see, we will spend quite a bit more time on that one. The sky looks blue because of scattering, and the sunset is red because of scattering as well. Scattering happens when light hits a particle, and that particle starts to act as a second radiator, redirecting the light, actually depending on the wavelength. Then we have reflection, so light bouncing off a surface back into our direction, the direction of the camera or the eye. And so often objects will have patterns on them, will have a certain color. That means if they look green, for instance, that means that object will reflect more green light towards us. That's reflection. And then finally, we have refraction. That is the amount of light that goes into the material. For instance, if you have a transition between air and water, light comes in, part of it gets reflected, part of it goes into the water and propagates there. That's refraction. Another example, dispersion by a prism. We saw that light being broken once it entered the glass. It changed its orientation. It was refracted. So we have seen that example. But we'll say also a little bit more about that. Something we will not talk about at all is this diffraction thing. Don't mind, this is all happening at the microscopic level. We are only dealing with interactions that have effects at the macroscopic level that we can easily see with our eyes, that are happening with real objects. Well, with objects that we encounter in our daily lives. First, we want to say something about scattering. Remember how light was occurring because there was a charge and it moves and it generates an electric field, and that then amounts to being a light wave. So scattering is a bit the same, but light comes in and light wave comes in, hits a particle, brings that particle into motion, because the electric field will exert a force onto the charge, brings it into motion, and that charge will then start to play the role of a new light source. It will in its own right send out light, emanate light, and that will happen typically in different directions. First, we want to say something about the size of the particle and the size of the wavelength of the light. Depending on the case, there will be 3 types of scattering going on. If a particle is very small, we get what is called Rayleigh scattering, and that is strongly wavelength dependent. So that's for very small particles, like in normal air. The particle is very small, even compared to the size of the wavelength of light. Then you can have the case where the size of the particles becomes comparable to the size of the wavelength. And that is an area where we have so-called me-scattering. Strange effects, but wavelength dependent, but complicated. And it was me, a physicist, to really analyze that in detail. And then finally, if you have very large particles compared to the size of the wavelength of light, you get some scattering, but it's all non-selective. And that means it's not dependent on the wavelength. So all the wavelengths are scattered to the same degree. So we have these 3 types of scattering, and we'll bring all 3 together in a single figure, like this. So in order to read that figure, it takes the size of the particle, the scattering particle, as a reference. And that size is given here as S. You can think of it as kind of a unit. So that's the size of the particle. And then different wavelengths will be larger, similar, or smaller. So for instance, on this side, the wavelengths which are on the axis, increasing wavelength, here the wavelengths are quite a bit larger than the size S. So that's where we will have Rayleigh scattering. In this area, we have wavelengths that are more or less the same as the size of the particle. That's the me scattering part. And then on this side, where the wavelengths are quite a bit shorter than the size of the particle, you have this non-selective scattering. So wavelength independent scattering. So you see the amount there is flat. Whatever the wavelength, same level of scattering happens. First to the part on the right hand side. So this is the wavelength, the Rayleigh scattering part. And you see that in that part you have this fall off of the level of scattering with wavelengths. Shorter wavelengths are scattered more and longer wavelengths are scattered less. The amount of scattering is vertical, right? So less scattering for the long wavelength. So if you look at normal white light, both of all these different wavelengths, it's the blue light that will get scattered more, and the red light that is getting scattered less, and the rest in between, green, yellow, and so on. The fall off is lambda to the -4, so it falls off quite steeply. Now, this Rayleigh scattering explains why, on a bright day, you have a sunny day, right? You have this blue sky, because it's only this the light is being scattered a lot that is not seen on the direct path towards the sun. So if you look at the rest of the sky, it's a very indirect path coming from the sun towards your camera. This is dominantly blue, because dominantly the shorter wavelengths, the blue light, is being scattered. The same Rayleigh scattering also explains why at sunset the sun is reddish. Then the sun is very low above the horizon, and that means that the light directly coming from the sun towards you has to cross through a long path of atmosphere. And that means there's a lot of scattering possible along the way as well. So most of the blue light will have been scattered away, and what remains is mainly the less scattered red light, the longer wavelengths. So the sunset looks kind of reddish to us because it's mainly composed of the longer wavelengths. Then let's go to the non-selective part of this diagram. So wavelengths that are smaller than the sizes of the particles. Again, this is something we can see in the normal atmosphere with clouds. So clouds will have water particles, water drops in them, playing the role here of the scattering particles. So the size S is here the size of a water droplet. It's huge compared to the wavelength of light. And so we have there that non-selective scattering going on for all the different wavelengths. That's why clouds look to us like being white or greyish, anyway, non-colored, because all the wavelengths undergo the same level of scattering. Now, if you move then to the last part, that part around the size of the particle, that is where, in fact, very strange things happen. We have shown that here with this wobbling effect. And you see all kinds of color happen. This is a bit of a rare occasion, but it has been observed, for instance, at volcanic eruptions. Pliny the Elder, when reporting about Mount Vesuvius exploding, has been also reporting about that, the Pompeii disaster. And he observed that at some points the sky was like green and yellow and orange. People declared him mad, but actually what Pliny the Elder was observing was me scattering. It's all very real. So, as comment, if you want to have little scattering in the atmosphere, try to get longer wavelengths. That's also the reason why in the example of remote sensing that we saw before, there was not the traditional red, green and blue, but we replaced actually the blue, the shorter wavelength, by near infrared. So something with even longer wavelength than we normally would be dealing with in an image. So, and if you go to the real deeper infrared, wavelengths are even longer and even less scattering happens. But near infrared certainly is very popular in remote sensing because remote sensing is all about observing the surface of the Earth through the atmosphere. And so you don't want to have too much scatter. Scatter makes images blurred, gives unsharp resolutions of the detail on the surface. So by having infrared or near infrared light, you have far less of that kind of haze. Whereas for blue, of course, blue scatters so much. Blue is a bad wavelength for remote sensing because it scatters all over the place. But you can play this game even further. You can go to even longer wavelengths with radar, right? So we get with even longer wavelengths, and there you can even see through clouds, right? You can start to see through clouds. You can look at the surface of the Earth in the Amazon forest, for instance, where there are almost always clouds. You can see through them with radar because you are far to the right here, so hardly any scattering, even for large particles like water droplets. Also note that we are quite fortunate that there is something like scattering going on, because otherwise either we would have direct observation of the sun and that part of the scene would be lit, but as soon as you would move in the shadow where there is no direct sunlight, no direct path between the sun and the point from which you observe, there would be absolutely no light at all without scatter, right? So you would have a pitch dark shadow if there would be no scatter. If you sit in the shadow of a tree, you can still read a book because of scatter, because some light doesn't really just go directly from the light of the directly from the sun to the observer. It is scattered in different directions. So this indirect light still coming to you even if you are in the shades. Okay, here an example of what I've been saying actually before. So on top you have this sunset, and you see that the farther away you look from the direct path to the sun, you get more of these shorter wavelengths. So up there you have blue on top, and then it goes to more greenish and yellowish because you're getting closer to the direct path between you and the sun, where less scattering happens. But the farther away you go from that path, the bluer it gets because the light coming from there is more scattered. The bottom is an example where we have this volcanic eruption example, where you indeed see even greenish light appear. Very weird effect. Note that on top again, you see also some clouds, and these are all an example of non-selective scattering, so no coloration actually. Okay, so far for the scattering part. Let's now go to reflection. In fact, the effect we are mainly interested in here. And we'll first talk about mirror reflection, so kind of speckle reflection, typical for very shiny surfaces, surfaces that are flat at the level of the wavelength of light, so very flat. And here you see examples of that. These types of specular mirror reflections. So here's the situation. We have two media. To fix ideas, let's say the top is air and the bottom would be water. Two different areas indicated by these two optical characteristics. The refractive index N1 and N2. Different because we have two different materials. Refractive index, we don't have to go into the details. Again, they appear in the Maxwell equations. They are dependent on the electrical permittivity and magnetic permeance of the material. It doesn't have to interest us too much here, but they differ between different materials. Okay, now light will come in from top left, hit the surface, and then get reflected back into the first medium. Actually, only in part, because a part will also enter the second medium. But that's refraction. We'll discuss that in a second. So here, light comes in. Then we have the normal to the surface, this N, the normal to that plane intersection between the two materials. Okay, so we come in under this angle delta I, and we have some electrical field vector and some magnetic field vector for the incoming wave. We can always write the electric field vector as a composition of a component that lies in that plane of incidence, this orange plane, and a component orthogonal to that plane. So we will have some orientation of the electric field vector. It will be orthogonal to the green line, to the direction of propagation, according to Maxwell's equation. And then we can decompose that always into these two components in the orange plane and sticking out orthogonal to the orange plane. We call these the parallel and perpendicular components respectively. Notice maybe a further word about the orange plane. It is actually containing that green direction of incidence and the normal direction. So these two vectors basically can be used to span that plane. Okay, this is the incoming light, and now part of it will get reflected back. There we go. That's the reflected light. It goes back into the first medium. So only part of the incoming light will be reflected, by the way. The other part goes inside the material as said, but it's second material. Here's the law governing that reflection, and it states that the angle of reflection is the angle of incidence. So we had that delta I before. Now we have this outgoing reflected ray going to the right, and that delta R, that angle of reflection, is actually the same as the angle of incidence. So delta I and delta R are identical. And this rule is independent of wavelength. Wavelength has nothing to do with that rule. For all the wavelengths, this is true under mirror reflection. Okay. In fact, we can play the same game for the outgoing, for the reflected wave. We can decompose its electrical field vector into a parallel component lying in the orange plane, and then also a perpendicular component sticking out. Why do we make the distinction between these two components, parallel and orthogonal? Well, because perpendicular, because they behave differently, these two components, dependent on the material. Here's what you get if you have a non-electroconductive material, a dielectric. So it's not conductive for electricity, for electric waves. For different angles of incidence, so for these different delta I's, from 0, which would mean we fall in perpendicular to the interface between the two media, to 90 degrees, that would be like a grazing angle. You come in almost parallel to the interface between the two materials. And angles in between. First thing to note is that, okay, if you come in perpendicular, there will be most of the light, it seems, will go through, because only like 10% or so is being reflected back from where you came. With grazing angles, the story is quite different. So if you come in very obliquely, under a grazing angle, you fall onto that surface. Most of the light will be reflected back into the first medium. And we know that from experience. We see that in physics over and over again. It's like if you have a space capsule and you want to enter into the Earth's atmosphere, if you come in under the wrong angle, you will be reflected back into space. Or if you have a rock and you throw it on water, then you can have the same effect if you just throw parallel to the water surface almost. The stone will first reflect a number of times and only then go under. And so this tendency to have a strong reflection if you just come in under very shallow angles, under grading angles, is seen all over the place. But then also in between, around 60 degrees of incidence, so a bit like that, that's about 60 degrees compared to the normal, you have also an interesting effect, because there the parallel component will die off. It's not getting reflected at all. No reflection. You see that the curve there for the parallel component almost going through zero, while the perpendicular component is, of course, not perfectly reflected, but quite a portion of it is being reflected. And that means we have polarized the light. So if you look at the reflected light, it only contains the perpendicular component. If you come in under that particular angle around 60 degrees, it's called the Brewster angle. So reflection can be used as a means to polarize light. You have to come in on that particular angle, and the outgoing light will be polarized. Okay. Now, it's getting even more interesting, because this effect that you have for dielectrics, you do not have for conductive materials, metals. So that is what typically happens if you have a good conductor, say a metal. Yeah, there is a difference between the perpendicular component and a parallel component in how far as they get reflected, but both are reflected pretty strongly. So this curve also amounts to what we know from experience. Metals are very mirror-like, right? So they are very, very shiny, they strongly reflect, and you see that across the board, quite independent of the angle of incidence here, you have very strong reflection, everything is up there. But there is no angle where you would have this strong qualitative difference between the perpendicular and the parallel component. Both always get reflected quite a bit. So, no polarization through reflection by metal. Okay, and this is something we will use, this effect, this difference between metals and dielectrics, we will use also to make the distinction between these two materials by well choosing the illumination and the polarization that we apply. Okay, now from these very flat surfaces, these kind of shiny surfaces, flat at the level of the wavelength of light, therefore very flat, to more realistic surfaces. Even if the surface may seem very flat to us, like the tabletop here, it is of course at the level of the wavelength of light, not quite so flat. So what light will see at its own level is more something that you see on the right here. So it's quite an uneven surface. And that means you could actually model that as different small pieces of surface with different orientations, each acting as a mirror. But by the fact that their orientations differ, even if the light comes in from the same direction, so you see here all that light coming in from the same direction, right? The reflection is going all over the place. So we have reflections in many different orientations. So if light being reflected in many, many different directions, even if all the incoming light is parallel. So here on the left, this very flat surface, all light coming in parallel, all light going out also in the mirror direction. That's the parallel, that's like mirror behavior, specular reflection component. This is more like a real surface would be like in nature, and even if flat. And you see that now light is being reflected in all possible directions. That's why we can also actually see these surfaces from wherever we are looking, because there's always some light being reflected towards us by those surfaces. So that's more like diffuse reflection model. And here you see an overview of how reflection can then be classified, you could say. So first is diffuse reflection, secondly specular reflection, and thirdly the more realistic type of reflections, which are this mixed model. So first, specular reflection. So you come in from the left in that direction, there you see the normal, and you know from what we have seen before at the very start of the discussion on reflection, that the light will be reflected in that mirror direction. So if you look at different orientations, you see a peak in that mirror orientation with the same angle of reflection as the angle of incidence, as we saw. So if you move a little bit out of that direction, it's not like there's an immediate drop off to absolute zero. In practice, there will be a strong fall off though. You see, if you move the orientation of that line right a little bit, the intersection with the red area will be shorter, will be less reflection. Whereas if you have a diffuse surface, so again, light coming in from the left, there you have the normal being drawn, and then depending on the direction from which you observe, you have as an amount indicated this red part, and you see the intersection between that hemicircle and the different directions of observation is almost the same, which would mean this surface looks equally bright from wherever you look at it. And that's a typical diffusion, actually Lambertian surface in that case. Lambertian reflection is a special kind of diffuse reflection. And in particular, Lambertian reflection is the kind of reflection where the intensity that you observe is completely independent of the viewing direction. Not of the illumination direction, only the viewing direction. So that's the kind of typical diffuse reflection. So diffuse reflection, specular reflection, but most surfaces are in between. They will have an amount of reflection for different orientations like you see there. So there's quite a bit of reflection in all directions, but then a bit more in the mirror direction, like with specular reflection. So you see that kind of second lobe sticking out there, where you have more reflection in those directions. And that's a typical behavior for most real surfaces. So coming back to this table, it's a little bit shiny. And that shininess is a specular component, but it's not like it disappears when I'm out of the mirror direction for the incoming light. It's always visible to me because it reflects light in all directions. Okay, that's for real surfaces. So they are in fact composed of all these very tiny mirrors, you could say, and that gives you this more diffuse reflection. How about wavelength dependency? Indeed. So we have been discussing a lot about the direction of the reflection and maybe also about the relative amount of reflection for different polarization components. But how is wavelength? Well, again, the amount of light being reflected by a surface, especially by the diffuse component there, will be dependent on the wavelength. That's a property of the material the object consists of. So some wavelengths may be reflected more than others, and that gives the object its color. So if you have an object we would call green, it means that it reflects more of the green part of the spectrum towards us than of any other part. Here's an example from plants. So different wavelengths you find on the abscissa, the amount of reflectance you find vertically. Now, this may be a bit misleading because not the entire part of the spectrum shown here is visible. So only from 400 to about 750 nanometers, that is the visible part. That's what we as humans would be able to see. You see this peak around 500 nanometers, 555 nanometers. That's green light that's mainly being reflected to us. The plant looks green. But then there's not so much red being reflected. That's a dip. And immediately after that dip, when we enter into the area of the near infrared, the part that we can no longer see with our eyes, we see a strong increase in the level of reflection. This is called the red edge, by the way. The contrast between the amount of reflectivity, reflectance for the near infrared and the red. That contrast is typically big for a healthy plant. If the plant is not so healthy, it will reflect also a lot less in the near infrared region. And that is then a good sign that something is wrong. So people in agriculture will use that quite a bit. But you see here that dependency on different wavelengths for the reflectivity. That brings us to the diffraction, so the complementary part of the story. We know it all from experience, like in this example of an air to water surface transition. You see the bending of the light. So light does not enter into our field of view, into our camera under the same angles anymore. So, coming back to the figure that we saw before, so suppose indeed, again, top is air and the bottom is water. Light comes in. Again, you have this orange plane of incidence, and then part of the light is reflected, we discussed that before, but part of the light is also going into the second material. And notice we can play the same game, we can decompose that incoming wave with a parallel component and an orthogonal perpendicular component and so on. But we won't go into the mathematics of all that. How much is being refracted depending on the state of polarization will not be of much interest to us, so we won't deal with that. But notice that there is something going on with the angle of refraction. So we have delta I before, the angle of the incoming light relative to the normal, and then we get this transmitted light here, this delta T, also its own angle, the angle of refraction, that is. And we see that these two angles follow a law, but it's no longer angle of refraction is just angle of incidence as we had with reflection. No, this is much more complicated. Now we have N1 times the sine of the incoming angle is N2 times the sine of the refraction angle. Well, it's more complicated, okay? But even more important than that is that this M value, the refractive index, is actually dependent on wavelength. And what that means is that since these refractive indices are actually not the same for all the different wavelengths, the angle of refraction will also not be the same. So even if the light nicely comes in as white light, all under the same orientation delta I, different wavelengths will be refracted under different angles. And that's of course what made the prism work before, right? How we could see that the light was actually composed of the different wavelengths was because of this effect. Snell's law, it's called. So the angle of refraction is a function of the angle of incidence, but also of the wavelengths through N1 and N2. And these have huge consequences for optics, because as we will see, we'll use refraction quite a bit when we are using lenses. Lenses use refraction for image formation. And here we see a problem. Different wavelengths don't behave the same under refraction. If we would only be able to build our cameras with only mirrors, because mirrors do not have that problem. Remember the law for reflection, before, where the outgoing angle, the angle of reflection, was just the angle of incidence. So there we have an equality independent of wavelength. Here, no longer. If you could build cameras with mirrors, we would not have that wavelength dependency, but now, since people use refraction with lenses, we do have it. We saw this example already with the prism, and here you see again, top left, how that effect is actually seen. So you have incoming light, but then the light that is refracted depends on the wavelength in terms of the direction it takes. So the red light is bended least, but then the shorter wavelengths are actually bended the most. A result of Snell's law. Then the last effect, I will not say too much about that, is absorption. So absorption means that some of the lights will be dissipated. Actually, some of the wavelengths will be dissipated. Which wavelength? Well, as we said, these waves consist of an electric and magnetic field. That electric field will start to exert a force on the charge, will bring the charge in motion that we have in our medium. Now, if the frequency of the light corresponds to resonance frequency of that charge of a molecule, it will start to flip around wildly, and it will dissipate it will dissipate all the energy of the incoming light. So that means that wavelength with that resonant frequency will actually just disappear. It's absorbed by the medium. So it's like taken out of the spectrum almost. So here you see the effect. So we have these very narrow windows of these resonant frequencies where the light with that wavelength, with that frequency, is actually absorbed away. So the level of absorptance will be something like this. Close to zero, then suddenly going up for that resonant frequency, going down again. There's another resonant frequency for another molecule, there it goes up again, so that molecule will also take out. The different molecules with different resonant frequencies take out all these chunks, these little parts of the different of the spectrum. Here we have a curve with different wavelengths of sunlight. The top curve shows, in fact, the composition of sunlight above the atmosphere in terms of different wavelengths. The lower curve does the same, but below the atmosphere on the Earth surface level. And you see the difference is that, okay, there are all these gaps now, right? So these are these additional undulations, and that's the effect of absorption. So there are all kinds of molecules in the atmosphere, and they absorb selectively certain parts of the incoming light. So it's like they take out parts of the spectrum. That's the effect of absorption. Notice, by the way, that if you look at what reaches us, the black line below the atmosphere, the peak is around 550 nanometers again. That's also where human vision is the most sensitive. So we are most sensitive to the light that we get from the sun. So, and this ends the first lecture. I thank you for your attention.